So we're going to do this example where we have an inclined plane. And we're going to have some mass on the inclined plane. But we're not going to have any friction. So I'm going to put a block of some kind. So there's my block. I also have a block hanging. And we're going to have a pulley which attaches these two objects. And then we have to take this and we have to rotate it around so that it's parallel to the surface. There we go. So then we attach a rope to this, put it up here, and then the rope comes over and goes down there. We need to move this over to center it. And just like before, let's make M2 equal to 5 kilograms and M1 equal to 2 kilograms. And we're going to have an angle theta. And let's just do it for a general angle theta, see what happens. We're assuming that the angle theta is small enough. Well, even if the angle theta was, even if these two masses hung straight down, it's still going to go this way because this mass is smaller than that mass. So this will be good for any angle of theta. If theta equals 0, then we go back to our previous case of the flat table. And so our equation should be such that when theta equals 0, we go back to the original case. Okay, is there anything else we need to do? Okay, we're going to say no friction at this point. So we draw free body diagrams of the two components of this system. The only thing that really connects these two things is that rope. So we don't really, and so the rope connects it. What that means is the tension is the same and also the accelerations are the same. So here's our inclined box. So what forces do we have acting on it? Well, we have a weight that goes straight down. We have a tension which goes in this direction. We define the coordinate systems as such. So I'll call this x1, y1. And we have a normal force that's pushing this direction. Normal to the surface. That's what's called normal force. This force here can be broken up into a y component and an x component, so we can do the things separately using the principle of superposition. So let's call this F sub n1. We'll call this W1. This is the angle, which is angle theta. Well, if you think about it, if this thing rotates around, this angle is going to get smaller. So this is theta. And when this thing is horizontal, when I rotate it counterclockwise, it's going to be flat. Theta will go to 0. So that's the right one. So this is going to be, we're going to call this W sub x1 and W sub y1. And we'll call this T. So some of the forces in the x direction, it's actually moving in that direction, so there's an acceleration. And we have two forces acting on it now. When we had a flat table, we just had one force when it was frictionless. So we have T, which is going in the positive x direction, and we have W sub x1, which is going in the negative direction. We also have the sum of the forces in the y direction. It's not moving in the y direction. And what we have there is that we have W sub y1 and the normal force. W sub y1 is in the positive y direction. No, it's the other way around. W sub y1 is in the negative y direction. And the normal force, F sub n1, is going positive direction. So some of the forces in the y direction are just telling us that W sub y1 equals the normal force. Again, we don't need this for this particular calculation. We will when there's friction in the problem. So we really only have one equation of that. Now let's do the next. So the next body is this thing hanging down, and it's exactly like in the previous problem. So you have the weight that's pulling down, and you have the tension pulling up. We'll make the weight larger than the tension so it moves downward. Let's define y positive going up here. So we'll call that we'll call that y2, and this is x2. There's no forces acting in the x2 direction, so we don't have to even write it down. So let's give this. This is the tension. This is W sub 2. W sub 2 is equal to M2 times G. Just like over here, W1 is equal to M1 times G. And if we sum the forces in the y direction, it's equal to, this thing's moving up and down, so we have the mass, object 2, and I forgot the subscript 1 over here, so put that 1. Okay, so we have M2 times A sub Y2 is equal to the sum of the forces. T is going up, W2 is going down. So let's write the equations we know. So from the first body, we know that the sum of the force, well, we don't have to do the sum of the forces. Let's just do what we have left over here. So that was M1 A sub x1 is equal to T minus W sub x1. Okay, so that's one equation. Second equation is this one. M2 A sub Y2 is equal to T minus W2. So our knowns are M1 and M2. Our unknowns are A sub x1, A sub y2, T, W sub x1, W2. So we have 5 unknowns, 2 equations. So we need 3 more equations. Well, here's one of them. So let's use 1, 2, 3. So the third equation is W2, weight 2 is equal to M2 times G. Okay. We also know that W sub x1 is equal to W1 times the sine of theta. So we've actually introduced 2 more equations, 2 more unknowns. We don't know what W1 is, and we don't know theta. So now we need 1, 2, 3, 4, 5, 6, 7 equations. Okay, so don't worry, they're there. So W1 equals M1 times G. Okay. What else do we know? Don't know. Oh well, we do know theta. Sorry, we're given theta. Well, we could be given theta. Okay, we're gonna keep it as a variable, so we don't. So we only need 1, 2, 3, 4, 5, 6. So we have 5, and the other one is the relationship between the accelerations. So we again, A sub x1 is equal to negative A sub y2. So those are my 6 equations, 6 unknowns. And then we just have to start substituting. So we can substitute that one in there. So that'll become M1G sine of theta. We can substitute that into there. So let's draw some arrows here. So this one will go there. This one will go there. We already used that one when we went this way. And then this one will go, go there. So let's make those substitutions. So we have m1 a sub x1, but that's equal to negative a sub y2. That's equal to t minus w sub x1, but w sub x1 is equal to m1 g sine of theta. Okay, so that's the first equation. Second equation, m2 a sub y2 is equal to t minus w2, the weight, but that's equal to m2 times g. So again, we're going to solve for the acceleration. So we have to solve for t from one of these. So this one's the closest one, so let me do that one. So t is equal to m2 a sub y2 plus m2 g. Okay. And then we could substitute that into here. So we'll get the left-hand side will just become minus m1 times a sub y2. The tension plugged in there will be m2 a sub y2 plus m2 g. And then I subtract m1 g sine of theta. So now we only have one unknown, which is a sub y2. So I'm going to move this to the other side. So I'll have negative, the first term is this one, m1 a sub y2 minus m2 a sub y2 is equal to, well, I've got this term still over there, m2g minus m1g sine of theta. So I factor out what I'm looking for. I've got m minus m1 minus m2 is equal to m2g minus m1g sine theta. I'm going to divide by, get the negative sign out of there. So what that'll do is it changes the sign here. So you get m1g sine theta minus m2g, and then divide by the sum of these two. So that's your answer. Now I said, let's go back here, when theta is equal to 0, this thing should revert back to what we just did in the previous problem. So let's just check that out. If theta equals 0, sine of theta equals 0. And so we get a sub y2 is equal to negative m2g divided by m1 plus m2, which is what we had previously for the special case of theta equals 0. We also have the case if theta equals 90 degrees, sine of theta equals 1. In that case, a sub y2 is equal to, well, this becomes 1, so you get m1g minus m2g over m1 plus m2. So what is that? What's happening in that case? Well, what you have is a pulley, and you have two masses. And we'll do an experiment, or we will have done an experiment in class that does this particular scenario. So this comes down, this comes down. You just have two masses that are hanging. This is called an Atwood's machine. So in our case, this was 2 kilograms. This was 5 kilograms. So this one contributes to, this one wants to make it go clockwise. This one must make it go counterclockwise. If this is bigger than that, then it's going to turn clockwise. If this is bigger than that, it's going to go counterclockwise. If they're equal to each other, then the numerator is 0 and it just sits there. So if this is 5 kilograms and that were 5 kilograms, nothing would happen. To accelerate the system, though, you have to sum the masses together. So the total inertia is 7 kilograms, or the total mass is 7 kilograms. So the difference in the masses determine how fast it goes. The bigger the difference, the faster it goes. But the bigger the mass is, the total mass, the slower it goes. So if you had 200 kilograms and 500, or 200, let's say you had 202 kilograms and 205 kilograms, the difference would be the same, but the denominator would be much bigger, and therefore the acceleration would be really low, would be really slow. So let's kind of go back here. You break both of the objects. So here's your original scenario. You do 2 free body diagrams, one for this block, one for that block. The thing that connects the two is the tension in the cable and the fact that the accelerations are equal in magnitude. You define your coordinate system so that x is parallel to the surface and y is perpendicular to the surface. Your tension is parallel to the surface. Your weight is going straight down, so you break that up into 2 components, one that's perpendicular, one that's parallel. The angle theta of the incline is this angle, so this is going to be W1 times the sine of theta, because it's the opposite side, and this is going to be W1 times the cosine of theta, because that's the adjacent side. So we sum the forces in the x direction. We have positive tension, because these 2 arrows are pointing in the same direction. This is in the negative x direction. So we get the sum of the forces equals the mass times the acceleration. And we do a free body diagram of the hanging mass. You have tension pulling up and the weight pulling down. Because the weight is greater than the tension, is going to pull this, the net force is going to be downward. So in applying Newton's second law, here the mass of this second object times its acceleration is equal to the sum of the forces, T positive, same direction as y, W negative, opposite direction of y. So we ended up with 2 equations, but I think originally 5 unknowns, so we needed at least 5 equations. W2 is equal to the mass of the object times acceleration due to gravity. The x component of the weight for object 1 is W1 sine theta. W1, the weight, is the mass of object 1 times g, so I substitute this into there to get that. I have one extra equation. I have one extra unknown here, so I had to come up with, I think, one more equation, which was this acceleration thing. We always have that relationship between accelerations, so make sure you do that. So I substituted that into here, then that into there, this into there, and this into there. So those 3 substitutions just give me two equations and 2 unknowns. I solved the second equation for T, the tension. Then I plugged it into the first equation for T. So this equation becomes that equation. The only unknown is a sub y2. So I bring that over to the left-hand side, make it negative. I factor out my thing I'm trying to solve for, which is acceleration. I divide by this, but I go ahead and switch these 2 because I'm going to multiply by -1, so that's good on both the numerator and the denominator, so that flips these around, and I get that. And there were the 2 special cases of theta equals 0, which is what we worked previously, and we got the same answer. And the case where theta equals 90 degrees, which is this situation, and you end up with this because theta is equal to 90, sine theta is equal to 1.